We're going to go ahead and get started. Hello, functional programmers. Welcome to the 8th lecture, Polymorphism. We've got the house points up here. Remember, just to show you every single week, that yellow is only 10 points behind, which means that if yellow wins this one, and then also they win the next one, or the next, wait, I think there's 3 left before the next voting. So if you have time, I believe that even House I Love Brandon has a chance, okay? So you gotta pull it in to get it today, alright? You've got it. But besides that, today we're talking about polymorphism. I wanted to mention to you your exam. You have your exam. When do you need to show up? Monday. Here, it'll be in this classroom, 80 minutes to take this examination unless you have other accommodations, okay? But it will be on a Monday, which is not a day that we usually meet, okay? So remember that. Show up. If you don't show up, it's going to make both of our lives significantly harder, okay? Which you don't want, okay? What time is it? Same time as lecture. Yes. Yeah, it'll just be in the same place, okay? Yes. Okay, so the past few lectures we were talking about a lot of stuff that was... there was a lot of me standing up at the board and solving equations in front of you, okay? Which is not necessarily the most exciting thing, but it's all in the pursuit of this idea of the fact that we can analyze our code and we can give mathematical grounding to how we think about the complexity of our code. But that complexity is not the only place we can give that consideration. Remember the things I said on the first day of lecture. What do we want? We want descriptive code, we want modular code, and we want maintainable code. Today, we're going to be going back to our roots and talking about stuff that's way more in line with that, stuff that's in keeping with those ideals when we talk about polymorphism, which is a way of kind of saving us some labor when we do programming, okay? A way of writing more descriptive code in a more fundamental way. Who here took like AP, CSA, and knows of polymorphism from there? Raise your hand. Great, put your hands down and forget everything that you learned from there. This is completely unrelated, all right? It's called polymorphism, it's not the same, all right? Yes. Yeah, okay, and this is the lecture where I usually start to introduce, well, I mentioned her before, but this is Polly, the polymorphic parrot, and he's our mascot for this course. They are 3, actually, this is one of them, but polymorphism, Polly the polymorphic parrot, today you will see why that is. Alright, so let's go ahead and get started. Well, I'm going to need to disconnect this because sometimes this side. Oh, there we go. Oh yeah, and someone left feedback, really good feedback, that I should put the Mendy code at the beginning of lecture. So copy this down real fast. You can ask anonymous questions over the course of the lecture, and once we recoup at halftime, I will go through and answer those questions. We also have a lovely faculty mentor, Dilson Kanar, here today, so make it one so it can make me look good, all right?
Really quickly, is your microphone on?
Is it on? It probably is not. Thank you so much.
Okay.
All right, thanks, Alexa. Okay, cool. Everyone good at this? Remember, you can ask anonymously at any point. Okay, we'll move on. Okay, so our lesson plan for today, we're talking about a few things. We're going to give type inference a little bit more of a concrete treatment today. We'll talk about this idea of polymorphism, but parametric polymorphism. We'll talk about how we can make our data types also parametric in that same way, and then we'll talk about how we can redo the sorting we did last lecture, but now polymorphically. And it's okay if none of that means anything to you right now, because in 1 hour and 20 minutes it will. Okay, all right. So this last time is pretty unrelated, but remember that we talked about runtime complexity, we talked about the tree method, and we talked about merge sort. Okay? All right. Type inference. So type inference is something we've already talked about a fair amount, but it amounts to how SML is able to ascertain whether or not something is well-typed, what type it is, and whether or not it's ill-typed as well as a corollary of that, right? But one thing that we've been doing this whole semester is we've been type annotating everything, and we've been using ints all the time. It's been insanity. It's been never-ending. It's been insufferable puns, but it's been awful, right? Because we keep writing these functions, and we're localizing them at this type of ints. For instance, suppose I had the length function, which we've written several times this semester, and the whole semester so far I've been writing of type int list, and then returns type int equals 0, and then length of x cons x's is shouted out. What is this? I was writing it as you were saying it, but yes, correct. But if you notice, I didn't use this x, right? And I told you about patterns, how we use the wildcard pattern to discount things that don't actually matter to us. So for all intents and purposes, I could have written this. And what I mean to convey to you here is that we don't actually examine the x in front of this list at all. we never do anything with it. So I've type annotated that int list. But what if I wanted a length function on string lists? Well, okay, let's do it. Let's do fun length string, and we're going to take in, string list. We're going to annotate it like this, and it's going to return int, so we'll say 0. And then someone shouted out to me, what is the recursive case of length string? Sure, length string x is plus 1. We can permute the plus if we want. But now I want a length function on bools, and now I want it on lists of lists. I want it on 2D lists. I got to write another one of these. That's terrible. It's painful. It's redundant. And worst of all, remember, it's ugly. Okay? And we don't want that. So I want to be able to not have to do these things. And as I'm very heavily implying to you right now, we are going to be able to do that. Okay? But notice the form of this code, right? Look at the contents. Ignore the name, right? Ignore length string and length. They look pretty much identical, don't they? Like if I wildcarded this, and unfortunately we wrote it the other way, but if I put the 1 plus here, it would be pretty much identical, right? Except for the type annotations. So what the code does feels exactly the same, regardless of whether or not it stores an int list, or a string list, or a bool list, so on and so forth, right? So I want to be able to somehow write code that acts generically in this without having to deal with writing it over and over, right? Otherwise, I'd have to redo every single lecture up until now, but change my int list to a string list, okay? And then I'd tell you that you were getting, new content, and then you'd be charged like 20K for that, and you'd be pretty unhappy, all right? We don't want that. So let's not do that. So I already talked about all this stuff, but let's say this, okay? Let's talk about how SML is able to determine the type of expressions. Remember that we can definitely always find that type, right? We can find the type of something, but how do we do that, right? So recall that, like, for a particular example, and I believe, okay, actually, let me talk about this. So remember that the way that we do type inference is we just straightforwardly look at each component of an expression, and we apply very simple rules. Like plus has type int star int to int, meaning it takes in 2 ints and returns to us an int. If we have a contradiction, that's ill-typed. And then if we find a type, then we've got the type, right? So for instance, if we're doing 2 plus 3, well, we know, plus is of type int star int int. So what do we want to be true? We want this to be true if this is true, which it is, and if this is true, which it is, right? Very simple, not contentious, really. But we just look at each subcomponent, and if this was itself like 1 plus, we'd apply this rule again. You can think of it as, right? And that's just how we would do it. But let's talk about a little bit more interesting of an example. When we're talking about like bare values, like values that just stand on their own, this is pretty simple. We just apply the rule. What if I had something a little bit more complicated? I had a function which looked like this, okay? And the problem with functions is that they take in an input, and we don't usually type annotate them. So the type of the input could be anything. So let's do it. Well, how am I going to do this? I'm going to assume that x has some type. I don't know what type, but we're going to say that the x's type is a box. It's an unknown. And then what do? I go from here to here. And in this expression x plus 1, I remember I have this rule right here. So then it should be true that whatever type x is, it matches to this, right? So first of all, we verify that x plus 1, by the fact that that's a thing, that rule is a thing, has type int if we know that 1 has type int, which it does. And also we know that x has type int, which we don't know. But it's unknown. So let's set it. Why not? We're enforcing a constraint upon x. The constraint is that x actually has type int. And then because we have no other claim to what the type of x should be, because we have no other aspirations there, then it just is. Sure, let's retroactively backpatch what the type of x was. Okay? So this gets a little bit more complicated in the function case, but you should still be able to assure yourself we can still do it. Right? This is still fine to infer the type of. And to be clear, like we're assigning something to this, and then we're entering the body here is what you should think of it as, okay? Well, okay, let's talk about something a little bit more interesting, right? So everything happened to come up roses for us for that previous example, but what if it doesn't? And what is it? It's like x plus 1, x, string append, also 1, right? Yeah, okay. Well, here we're going to do the same thing. We're on the right, actually, I'm going to put it here. X has an unknown type. And then we want to say that this thing has whatever type of, a tuple type of whatever the left is and whatever the right is. So let's type check the left and the right. Well, x plus 1 is, again, this plus thing. So we say int if x has type int and 1 has type int, which this does. And that one, we're going to say, OK, so now we know that x should have type int. This is what we say a constraint. It's a constraint upon our type that is as yet unsolved. Okay? And then let's do this right-hand side. Well, remember also that string concat has type string, star string, to string, right? So then this thing should be of type string only if both of its arguments are of type string. So we should have the x's of type string, and then string 1 is of type string, which it is. So we're good here. But that's a constraint upon our x variable. We don't know, so we'll apply it here. So we'll say x is of type int and also x is of type string. Is anyone else thinking, danger, Will Robinson? Do we have an issue here? What's our issue? Yeah. I thought we said we were trying to make me look good today. Yes. I'm not going to comment on that precise comment, but this is terrible. Because why? Because this thing is of type int and also of type string. How can something be both of type int and also of type string? That should not be possible. Indeed, it is not possible. Okay? So, ill-typed. We will reject this program. Let me show it to you on the command line, actually, just so that you can see. But fn x goes to x plus 1, and then, x string append 1. Oh, what's this? Operand and operator do not agree, which by this point you're all very familiar with the fact that this means bad news bears, right? So we don't like that because it's ill-typed. So let's work on it. And note also, this is completely separate from the fact that if I'm just going to give it a really brief note that if I change this to plus 1.0, we'd still have an issue. Does everyone understand, like, this is plus on reals? Remember how plus can do on both ints and reals? We'd suddenly have, what would happen is that we'd go to here. And we'd still have an issue, okay? This is a special case. It's not anything related to what I'm talking about today, okay? Just not to mislead you in case you thought that this looked similar. But anyways, let's move on from that. But the point is that what happened earlier, I guess, a way of thinking about it is on this board, we had precisely the right amount of constraints, right? We had one constraint on x, which is that x is of type int, and then we ran with it, and we were like, yeah, it's cool, let's go. But here, we had too many, because now we have two constraints. We have a constraint that x should be of type int, and a constraint that x should be of type real, which is, or in the previous example string, but in this example real, which is bad. So let's try to work with, so we've seen two cases, like the right amount of constraints and too many constraints. I'm interested also in a different case. Can anyone actually predict what I'm going to say next? Like, what is another case we haven't dealt with? We talked about one constraint. We talked about two constraints. No constraints. What happens if I just don't have any information whatsoever about the type of my next thing? What about this one? Well, now I'm going to say, right, if I want to type check this, I'm going to say, OK, x is type question mark, question mark, question mark, right? I don't know what it is yet. And then I return, when I type check this, I'm going to use that assumption. So I'll say that my return type has type whatever that question mark is. So now I say this is type. I don't much like that. I don't think it's very clear. But in intention, that's kind of what's happening, right? We don't know what this type ought to be. This is going to emerge as a first-class property of SML programs that we can actually give a type for this. It's called a polymorphic type. Okay? Parametric polymorphism. different than the polymorphism you've seen in the past, different than Java, different than, I don't know, whatever other languages there are. Java's the only other one I know of. That's a joke. Parametric polymorphism is polymorphism out of working uniformly. The fact that your implementation is generic over whatever data you're operating on. Whereas polymorphism in a different sense is like kind of more ad hoc dispatching on, actually, no, I'm not going to try and describe what the other polymorphism is. It'll just confuse you. It's bad. We're going to see a better way to do it, okay? So there's this idea of an unspecified type, right? This unspecified type. But the type I take in and the type I return are the same. You would not say that this is type int to string, right? But it could have type int to int. It could have type string to string. It all depends on context. So we're going to give a name to this question mark type. We're going to call it a type variable. Okay? Different than the variables you've seen in the past, different than the variables that we've been talking about when we do variable declarations. A type variable is a variable that ranges over types. When I say ranges over types, it means that it is given meaning because we substitute for it with types. Okay, so here's what we're going to call it. Instead of question mark, we're going to call it tick A. Not A prime, not A apostrophe A. Okay? And this is going to be our type. This is called a type variable, and it's pronounced alpha. We typically pronounce it with the closest Greek letter equivalent. So this is alpha. This is beta. At this point, sometimes people say gamma. I feel like it's just strictly less useful to have to think about it. So usually I just say zeta, and I say deta, and then eta. You can keep this with this convention if you like. Probably the proper way to say is gamma, but I just say zeta. It's easier, all right? But you say the closest Greek equivalent, okay? And this thing ranges over types. It means that this thing can have whatever type I like, but these are correlated, okay? Every time I use this fnx goes to x, I can substitute this type with something else and obtain a type that it could be. It is now no longer true that every expression has exactly one type or can have exactly one type. You could possibly have a lot of types. This one could have type string to string. This could have type int to int. And this shouldn't necessarily be a foreign concept to you. Why? Because we've already been saying things like this is of nil is of type int list, right? Our favorite, ints. But also it's of type string list, right? In fact, we've had to tiptoe around this idea the entire semester, and today I'm going to be able to pull the wool out from over your eyes and explain to you what's really going on, okay? But this is the same sort of idea. So if your mind's breaking from this one type thing, it shouldn't, okay? We can do this anyways. Yes, okay. So one thing I wanted to say also is, why do I want to be able to do this? Why should I be able to have multiple types for one piece of code? Because isn't there the whole thing I said about types guide structure? I put it in bold on the first day. I put it up on the board. Isn't it misleading to have ambiguity in these types? But as you can see on the board, we're going to be able to use this for code reuse, and it's not going to break any of the safety properties we have about what we can do in SML so far. Okay? It's going to strictly make our lives better. All right, and you've already been benefiting from this, and you don't even know it. Okay, but if you have trouble, if you want to remember the motivation, remember, I don't want to write length a bunch of times. That should be the main use case you're thinking of in your head. I don't want to have to write that length function for every single type. Okay, so code reuse because an expression that has polymorphic type, that's the definition, right? It has a polymorphic type, like this is a polymorphic type, if it contains type variables. So these such functions that have polymorphic types can be used at a bunch of different types. So for instance, let's do this actually. Let me erase this for a second. Let me actually verify my sequencing. Yeah, okay, cool. Okay. Now I could write this identity function, and the identity function, remember, is the function that takes in something and gives it back. Okay? And I could write it such that it takes in an int and returns an int. This is something I could definitely write. Right? But you could probably see right by now, this is not something I want to have to do. This is terrible. I'm going to have to rewrite the identity function for every type. Let's not do that. Okay? So, finally, I'm so excited for this. You've seen me do this all semester, but we are no longer going to write type annotations. All right? In a lot of cases, you probably still should. It's good documentation, and it'll stop you from messing yourself up and then having to debug really bad type messages. But we do not have to, all right? I can perfectly well write this, and it'll take me less time to write these on the board from now on. And this truly does have type alpha to alpha, okay? So I'll just write like a comment. This is of type alpha to alpha. And what's that mean? What's that mean for me using this at the SMLNJ REPL, right? It means I can write this. I can write a val binding where I use identity on 1. And I can also write a val binding where I use identity on high. Both of these are allowed. I can do this. Let me demonstrate this to you, actually. So I can use identity on 1, and then I can use identity on high. Crazy. Code reuse. I don't want to have to redefine the same identity function over and over again. So I'm allowed to do this. This is perfectly fine. All right. So basically what I'm trying to motivate to you is now I don't have to write the identity function a bunch of times. I don't have to do this. I don't have to do identity string, identity bool. I just do identity, and I cover all my use cases. Yes. Yes. Actually, at a certain point, they start doubling up. Like you get like.
Okay, that was my question. Okay, that was my question.
It's not important whatsoever, but this does happen. Actually, I think it's inconsistent. There's some weird thing about the way it picks these names. I forget what it is though. But yes, that would happen. Fun facts that in Mulligan, the SML debugger I wrote, it's specifically hard coded so that I don't have to generate these names by saying that if you have more than 26 polymorphic types, it'll just crash because I don't want to deal with it. In practice, this never happens, all right? I'm an engineer. Leave me alone. OK. So the observation here we're trying to give is that the content's the same. The content's the same. The types are different. And that usually we want to let the content dictate the types. But in this case, the content is agnostic in some sense to the type, right? Here, we have this X, and we don't actually care. So this is the zero constraint case. We don't care about this, OK? So again, I've already kind of told you this, but this is parametric polymorphism, OK? Yes. Whoa, you're way far ahead. Okay, no. Well, actually, sorry. Wait, repeat your precise question, actually. No. Okay, an expression may, a value cannot. There's no value of type alpha. Let me explain this in a way that might make sense to everyone. So here's another way to think about this alpha nonsense, okay? We're trying to talk about a type variable that could be inputted with any types. Basically saying that for all types t, this is type t arrow t, right? So let's actually write that. So like if I have alpha to alpha, this is like pretty much the same as me saying like for all t, like types, and this is t to t. Alpha is a universally quantified type. It's a type quantified over every other possible type. So with respect to what he just asked, can I have, val x type alpha? What kind of type has type for all, or sorry, what kind of value has type for all t? Like it's of type string, it's also of type bool, it's also of types of bool star bool, right? Like this doesn't exist. We shouldn't have such a value because then I could put it wherever I wanted, and then that would clearly break my nice properties of type safety. So you're absolutely correct that this does not exist. But this does. We can't have something of type alpha to alpha, a value of type alpha to alpha. In fact, it's that one. It's that value right there. But we can't have a value of type alpha. Okay? Fun thing to think about. There's another meta-commentary thing I can say here, which is kind of like this. One of the coolest things about having these parametrically polymorphic types is like just looking at the type, you can get a lot of information out. Like if you look at the type alpha to alpha, I claim to you there's precisely one thing that does this, and it's the identity function. You get that just from the type. I won't go on for too long about this, but it's interesting, I think, and it's very useful about your types that they are able to describe the behavior just from looking at the type. And that's kind of what we wanted, right? We wanted to be able to say, if I see the type of this, I know exactly what it's doing, right? If I see something of type int list to int, okay, it could do a lot of things, but like my intuition is, maybe it's the length function, okay? So I don't know, I think that's kind of interesting. All right, but yes, good point. Cool. Okay, I already showed you this. So What we're looking for is we're looking for generic code. We want code that runs in many different circumstances, regardless of certain facets of its type. Okay? In other programming languages, they actually call this generics. In Java, for instance, they call this generics. They got it from the HUS. I'm not lying. They got it from ML. They got it from SML. Okay? So the next time you think that, oh, this resembles Java, nah, Java resembles us. All right? This is from like the 1950s. Like this has been a thing for a while. All right? Cool. Okay. And in particular, this thing I wanted to talk about is the kind of polymorphism that SML uses is called let polymorphism. Let polymorphism as in let polymorphism not be on your midterm next Monday, but also let polymorphism as in I don't actually think it's important that you know why it's called that. Okay, but it means that we only generalize a value as polymorphic after its bind site. Okay, and what I mean by that is don't expect a function to be polymorphic while you're defining it necessarily. If you constrain a function while you're defining it, you will constrain that function in general. Let me show you an example. This fails to be polymorphic. Okay, I'm defining the identity function, but within the identity function, I kind of like haphazardly use it on 5, and then I return x. Now, if you ignore what it's doing, right, if you kind of think about it with your brain, you might be like, oh, I take an x, and then I don't use this, so it doesn't actually matter, and I return x, so clearly this should be of type alpha to alpha, right? Because it takes in anything and gives it back out. Except right here, inside identity, I specified that it should take in an int. At this point, it was not generalized. It was not generalized in here. It was still an unknown to be solved. Okay? So then we'll say that this is actually going to be of type int to int. All right? Yeah. Well, yes, but we're talking about the types. Yeah. Yeah, the types are what's important. But you're correct that it would loop forever. Yeah. But in terms of the type checking, like it's not going to like this, and rather it'll like it, but it'll be int to int. Okay. Which is another comment. Like if you have type int to int, it doesn't mean you actually get back an int, right? Always. It means that if you return a value, it must be of type int. But everything we're talking about today is at the type checking phase, which means that we might come up with examples that loop forever. We might come up with examples that don't do sensible things. Doesn't matter. We're talking about the types. Okay. Good point. Okay. Does everyone understand why this is int to int? It's not like super important, but it's a good thing to know because you can trip yourself up with this sometimes. Yeah. So if I did like identity high below, that would not now fail the type check. Yes. That would fail to type check. Yes. The reason for this is because inside the body of identity, we're still figuring out the type of identity. That means that we currently have something which looks like question mark, question mark, question mark, right? And then you give identity int. So now we have, where x is of type int. So then that solves. But if we also add in the high, now we also have x is of type string. Fails to type check, similar to the examples we saw earlier this lecture, right? So basically, when we're in the declaration, we're still trying to find out the type. Afterwards, we get to play around with it as polymorphic. Okay. This is something like, as long as you have this general idea in your mind, I'm just trying to prevent you from like messing this up and then getting confused over why you're getting errors. But yeah, this is not like conceptually like super important, but good observation. Yeah. Okay. We'll move on. Cool. Okay. The identity function, though, I've been talking on and on and on. The identity function this, the identity function that. I don't actually really care that much about the identity function. And we don't really use it. And you might notice the ominous footnote saying yet, because we will use it in approximately 2 weeks. Quite a bit, actually. But for now, the identity function is kind of more of a curiosity, not something we actually do. But you know what is something we actually use? The length function. So right now, we can write the length function, and we don't need to specify the type at all. So I'm not going to write the length function back out, but someone want to hazard a guess for what the type of length ought to be? I don't think I said it yet. Right? What was that? What's wrong with it? So if length is type alpha to int, for all types t, it has type t to int, right? Suppose I want an instance of that, like int. Can we write this? Should this type check based on this? What was that? Alpha list? Is that what you said? Yeah, okay. So basically what I'm trying to show you is that alpha is a good guess, but it's not going to be quite correct because you can't take in any arbitrary input. You can only take in any kind of list, right? Because if I gave 0 to this, does 0 match to that? Does 0 match to that? No, it's not even a well-founded question to ask. You can't even ask whether or not it should match to list because they have different types. I'll keep this up. And you see now actually it becomes a lot more terse and nice once you no longer have to write the annotations. And this is what the engineer in me has been wanting to write like all semester. Like I've been salivating at the mouth to try and like not have to write these type annotations, and I remember I have to. It's a fact of the first few weeks of this course. But yes, so alpha list is going to be what we say is the right type. Okay? Yes. So is this a close slide? Let me see. No, it's not. Okay, so we're going to talk about this when we talk about instances, but there are types that are instances of this type. Okay, for instance, int list to int is an instance of this type because I substitute this alpha. But here's something else I could substitute alpha for. I could say beta star theta list to int. I could also say int list to int. When I say for all types t, I mean for all types t. This thing could be anything. It just depends on the context in which we use it. So for instance, this is a function that gives us the length of lists that contain ints. This is a function that gives us the length of any function, any list that contains tuples of two things. Okay? So this is actually a very useful type. And this one is something that counts the number of rows in a 2D list, basically. Okay? Yeah.
So like if we had a function like that performs similar to what like flatten performs, like it takes an intless list but can also take an int list, would that be alpha int list?
Flatten is generic. You didn't actually, it doesn't matter what the things were. So it would be alpha list to alpha list. Oh, sorry. So alpha int list isn't actually a type. If you have something that's like int list, so like this guy, this is still int list. It's a valid concrete type. It's not polymorphic whatsoever. It just is a list. It's an instance of alpha list, but it's not actually like this type itself. Yeah. But if you wrote flatten without type annotations, it would actually be polymorphic because it doesn't matter what kind of list. Yeah. Dependent on like a data structure that's dependent on like the type, like can contain things of multiple types.
Yes.
Yes. Give me 20 minutes.
Okay.
Yes. That's actually precisely what list is. That's how list is defined. I'm going to show you. I'm going to peel back the wool and show you how list is actually defined, in intention at least. Okay. But give me a second. Okay. So yeah. Okay. So for the next thing I wanted to do is I wanted to do kind of a little fun example with you, where we trace through how SML tries to figure out the type of something, because it's entirely mechanical. The thing I want to show you is that like there's nothing scary going on here, right? There's no magic. And you know, the earlier you discover that there's no magic to computers, like is the better for your education, I think, because we can understand it. Okay, so let's do this. I'm just going to copy this down. So foo is equal to, what is it? It's if A, then B plus 1, C, else D, right? All right. So let's try to type check this. Let's try to infer the type of this expression. So, no annotations to help me out, but I clearly see I've taken a tuple of 4 things, right? So first of all, let's fill in our assumptions, right? So A, before we put question mark, it's actually going to be alpha. We're going to give it at first a polymorphic type and then refine that assumption later, okay? And then B is of type beta, C is of type theta, and then D is of type theta, okay? And then at some point, we're going to want to come up with this type, right? Actually, I need the space. At some point, we want to come up with this. Alpha star beta star theta star theta. And let's just say I'm at eta here, okay? Because this is what we want to figure out, right? But right now, this is our best assumption, okay? Okay. So what do we notice? Well, what's something you notice? What's something we can simplify right now?
Yes.
A is a Boolean.
A is a Boolean, so let's write in a constraint. Because we use it on this if right here, right? Okay. What's another one? Yeah. B is an int. Right? B plus 1, yeah, so it's like an int, right? Cool. So B is of type int. All right, what's another thing we notice? Well, C we have here, but we don't actually, yeah. Maybe D is a function. D could be a function. But because we don't use it as a function, we don't know that for sure. Yeah.
What's stopping D from being a type?
Oh, sorry, did I mess something up? Yeah. Nancy. I'm missing a unit. I am missing a unit. I'm so sorry. You're absolutely right that it's a function. Thank you. I was going to give you a haiku anyways. Even though I'm the wrong one. Thank you. You know what? TAs get haikus too. Cool. Someone was talking and I interrupted them. Yeah. Because 1 is an int. And 1 point, if it was 1.0, it would be real, right? Yeah. Yeah. Okay. Cool. I need to give more haikus out anyways. So okay. What's another thing we notice? Not you. Yeah, that's like 2 observations. Yeah, but you're correct. Oh, sorry. You're correct that it takes in a unit. So let's do this. Where it's going to be of type unit to something, where that something is going to be whatever the same return result is of int and then whatever C is. Okay. So it'll be this. Actually, maybe I should be editing these in place. It'll be easier for me to show you. But int star theta, right? So these are going to be the same. And another cool thing is also, like, if I did this and then later on I noticed that C was like, if I did like this, right? If I did this, then we should update our assumption here, but also here, right? Because then D should also return whatever that is, okay? It's not just theta. It's going to be, like, dependent. But anyways, the example is not that complicated. But, okay. All right. So C, I just have here, yes. That's one of the stupid cases where I have to. This is one of the edge cases. I have to caveat to yes. It would be ints. They would both be ints. If SML doesn't know enough to infer, it'll just pick ints. It'll prefer to pick the int version of plus. This is not important. You don't need to know this ever. It's very sad that it works that way. But anyways, cool. Good question. Anyways, so is everyone convinced that like this is like as precise as I can get for C? Because I never really enforce a constraint on it. Like I use it. But like I kind of just like put it there and then leave it, right? I can't really get something more precise. Okay? So my end result is going to be, and we can work through all of this, all right? Blah, 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 blah. Look at this. I have a nice little graphic for you. We say that A is bool. Honestly, I don't know why I write on the board sometimes. I work so hard on making this look nice. B is an int. D is of unit to eta, we notice. But then that eta later becomes the same as this, right? Int star theta. Okay? Yes. It should have been brought up in lab. I never brought it up in lecture because I had better things to talk about. But unit, this thing, is the only value of type unit. Unit is a type that has exactly one value, and that's this guy. Left paren, right paren. That's pretty much all you need to know about it. Yeah. You can case on it. It'll just be a case that's pretty useless because there's exactly one case. Yeah. Thank you. Thank you. Oh my goodness, I didn't know this was a criticism, or not criticism, but yeah. All right, thank you. I don't know how to respond to this. I'm going to move on. Cool. And as you can notice, this is a very useful type. So our end type is going to be bool star int star theta star parens unit to int star theta to int star theta. Okay, because we return the same type as this. Oh, that's another thing we should say now. This will be the same as this eta. Okay, because that's what we end up returning. Is anyone confused about this? I hear murmuring. Okay. Okay, so not quiz time yet, but first I wanted to look at Menti, actually. So if you had any questions, why are functions values? Because they are. Actually, I'm going to answer precisely that question later this lecture. Will Friday's review session be recorded? TAs, can we arrange that? Like Zoom or something?
But
Slides will definitely be posted. We'll try for the recording. It's a little harder because we're not going to have like a videographer. It'll just be like on Zoom or something. So, but yeah, we'll see. Yeah. Okay. Cool. Yeah. All right. Let's move on. All right. Get up. Stand up. Come on. Stand up. I want to make sure you're awake as well. I'm looking in this direction. All right. I feel like people are mostly wrapping up. I know some people also left the classroom, but unfortunately, you know, that's how it is sometimes. There was a period this semester when I toyed with the idea of giving you more breaks and then doing 3 lectures a week. But I realized that it's really hard for me to like go in depth on something in like 50 minutes and then not say all the things I want to say. So I didn't do that. But that's just something I felt like I'm working on. Something I should also tell you is that the reason why the passcode is Iago is at my company, SemGrep, where I work, my mentor's name is Iago, and Iago is a parrot in Aladdin. So they're keeping with the whole, yeah, you know, I'm going to tell him that after this lecture. Yeah, what's up? Do you not?
No.
Yeah, he squawks, he's on Jafar's shoulder. It's like, hello, how am I going to become Sultan? Because you're going, he's voiced by Gilbert Gottfried. Yeah, that's right. Gilbert, I don't need to answer that question. Okay, all right. I should have put that on the quiz. Do you know who Gilbert Gottfried is? Anyways, okay, let's move on, shall we? Okay, we're going to talk about parameterized data types, which are essentially the things you've seen all semester, but better, all right? So we've seen we can have these polymorphic types like alpha to alpha and alpha list to int and so on and so forth, but we haven't had to like make them. We haven't had to like define them. Alpha list just kind of existed. Oh, something to tell you also, this is of type alpha list. Nil is not just of type int list and bool list, it's also of type, in particular, it's of type alpha list. Okay, but we haven't seen how we can make our own types that are parametric in this way. And we're going to see how we can do that right now. Okay, so what do I mean by that? So a parameterized data type is a data type that is declared with the type parameter. So basically, it is a type that depends on a explicitly specified type parameter. And list and option are actually examples of this. So let me show you. So if I wanted to define list, okay, and this isn't actually how it's done because it's like kind of hard coded in, but this is, for all intents and purposes, this is exactly how it's done, and you can write this. This is real SML syntax. Data type alpha list. Okay, I'm gonna take away the real SML syntax part, but yes, nil or cons of alpha star alpha list. All right. So what I'm saying is that this data type, alpha list, is expressing a lot of types. It expresses the type alpha list. It defines the type int list. It defines the type bool list, so on and so forth, right? It's defining a lot of types of this list type constructor taking in a type parameter, okay? And in particular, the constructors for the alpha list type are this default constructor, this constant constructor nil, or also it could be cons when you take in something of type alpha and something of type alpha list. But remember that these are linked in the same way that in the identity function they were linked. So it would not be correct. It's still not correct to say something like this, okay? I can't cons one onto the list of true because this is a type bool list and this is of type int, right? So I realize this is kind of backwards, but this is, I don't have room to write it the right way. In Soviet Russia, type has u. But the bool list here does not match that int, okay? So I can't do this. These have to be the same type, all right? But this is like pretty much exactly how you define it in SML, all right? Let's see. And okay, well, I'm just going to erase this real fast so I can write the other thing. And let me also define options for you. This is something that's also defined at the top level. But if you really wanted to define your own, you had a hankering to do that, you'd say similarly, type alpha option, and this is a space I'm putting between these two things, space, space. Alpha option equals none or sum of alpha, okay? Because an alpha option can either be the constant constructor none, or it's sum taking in something of type alpha, right? Yes. Yeah, okay, let's just assume that somewhere someone else put this. Ignore the part about this being real SML syntax, because you wouldn't actually want to do this, because I'm pretty sure it wouldn't accept this as a name. Or maybe it would. Maybe. I don't care is the idea. But yeah, it might be. This gets into stuff about how you declare infix operators. It doesn't matter. I could have written like nil and cons and gotten across the same idea. Okay. In intention, this is what it's defined as. Okay. But you could actually do this. And then, yeah, you could actually do that. Okay. I was going to say something. I forget what it was. Oh, yeah. In SML, none and some are capitalized. In the language I work in, OCaml, it's actually none and then some. So every time I write SML, I'm like, oh, it's so angry. It's yelling at me. None, some. But it's, yeah, this is not important. Okay. So this is intention how we would do alpha list and alpha option. I am the Wizard of Oz. I am the man behind the curtain. I'm showing you. This is what's been happening the whole time. Before, we've always had to say, for any type T, cons is type T star T list to T list, right? And it's been so annoying. We've had to just write that all over the place. And by that I mean like probably twice. But now this is what it is. It's just alpha. It's just alpha. All right. Worth noting the name of this type doesn't matter. I could have put of beta. That would have been fine. Doesn't really matter. Okay. It's just what matters that it is a variable. It is a type variable. Okay. All right. And yeah, so this is the reason why lists and options can contain types of anything or values of any type. Yeah, so that. All right. Cool. I already told you that. Cool. Let's see. So I already said this too. Here's the cool thing. We can also define polymorphic trees. And I'm gonna talk while I write it to really reiterate my point. But we can do polymorphic trees because before we've just been doing monomorphic trees. We've been doing trees that only contain ints. But now, and this is like something you'll actually see written in your code from now on, okay? Data type alpha tree equals the constant constructor empty or node of, and this is gonna get long actually. It always is. Alpha tree star alpha tree. So now a valid type is like int tree or bool tree or int list tree, which is a tree that contains lists at each of its nodes, because why not? You might actually want to do this. But note that if I did this data type declaration, tree is not a type. That's not a type because it expects a parameter, right? There's no like implicit thing going on. You have to, when you declare a polymorphic type, you have to give it a type parameter for the thing that it contains, all right? Always, yeah. I can't do that. I can't use type variables here if I haven't explicitly introduced them here. Oh. Okay. There's some subtle reasons for that, but yeah, it's not super important. But yeah, that is a restriction. I can only use the polymorphic type variables I've captured here. This would be possible, for instance. I could do that. Yeah. Yeah. There's not a whole lot of reasons for why you'd want to do something like that. Yeah. You can indeed. You can have an alpha tree. Or actually, maybe let's make it more concrete. You can have an int tree. Yeah, you can. This actually, I think this causes a lot of theoretical problems with the fact that you can this polymorphic thing can just be like the type you're currently defining. I haven't done that in a while, but yes, you totally can. There are reasons why you'd want to. There are. Like I've thought of a few, but yeah, none you'll see in this class. Okay, it's a little. That's where we get a little esoteric. All right. I think I actually explicitly have. Oh, I do. Yes. So if I had node of empty, comma empty, comma empty, that's actually of type alpha tree. Because, the thing that's stored is the empty tree, right? Why not? Why not? Generalization upon generalization. Remember, computer scientists were mathematicians first, all right? That's how it goes. Cool. So this is how we define trees, and this is something useful you'd want to do, all right? And in fact, because we have polymorphic trees, we can have trees with strings at the nodes. So you might see something like this. And if you do take the in-order traversal of this tree, something interesting might happen. Whoa, foreshadowing. But anyways, let's move on. Oh yeah, and that meme is like the future if blah, 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 blah. Yeah, this is the future if we had polymorphic trees, which we do. Cool, okay. So the fact that we can write these polymorphic data types means that now we can do cool polymorphic stuff on these trees. Remember our friend count? This always annoys me, this shadow thing. So we can write count that works on this new tree we've defined, right? Remember, count just counts the number of nodes in a tree. LXR equals count L plus 1 plus count R. And if you note here, we still don't do anything with this X, right? So I could very well wildcard it out if I felt like. But the point is that, like, irrespective of the data sorted in the tree, I care about what the form is. So this count function is, what do you think? What's the type? Any guesses? Yeah.
Alpha tree to int.
Alpha tree to int. Yes, that's correct. Okay. Oh, well, sorry. Correct. Alpha tree to int. All right, we can give it a type of tree, any type of tree. We could give it an alpha tree if we wanted. All right, we could give it the same thing we just showed. All right, it's a little. Actually, you know, let's do it. Why not? Star alpha tree, and then val x equals node of empty, 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 and then fun count empty equals 0, or count of node. Sorry, I'm just going to do this in front of you because I want to see this happen. Okay, so like count is of type alpha tree to int, as we saw, right? But if I give count x, which is of type alpha tree, we're going to get 1. Because an alpha tree, in particular x, has one thing in it, which is the empty tree. Cool? Feel like your mind's expanding? There's reasons to do this, I promise. I promise. Not the ones that we'll necessarily see, though. Okay? So for instance, I could define that count function, or this one. I wanted to do this one too. We can do, all right. So some of you are smart. In fact, most of you are smart. In fact, all of you are smart. But because you're smart, you know how to use Google, which is really bad for me. Okay? So you've been using this thing called option.valof, which I did not explicitly tell you. Please do not use that. I'm explicitly telling you right now. So option.valof is of type alpha option to alpha, which, by the way, if you ever see this type, you should check your wallet because bad things are happening, okay? But in particular, it means that if this is none, you get an exception. It tries to unpack what's inside the option, and if it's none, you get an exception. This is terrible. This is terrible because this is the same parse don't validate stuff I was telling you about like 4 lectures ago, which is that like you should just pattern match to get it out. Please don't use valof. Here's a safe one. We take in a default value and an option. If the option's none, we get the default value. Otherwise, we unpack the thing. Yeah. Get opt? Yeah, pretty much. Yeah. You can use. I mean, use pattern match. Just do it. Yeah. That's another library function. Okay. But does anyone actually hazard a guess as to what type safe valof has? Takes in a tuple, right? What's the left thing in the tuple? Alpha. I liked it. Takes in the thing inside, takes in an option that might have the thing inside. If it's none, this thing, we just give it the default value. Otherwise, if it's some, we unpack the thing inside. That's not important, but this is actually a pretty useful function to have. Get opt, yeah. Yeah. Anyways, random diatribe. Don't use valof, please. Okay, cool. Okay, all right. So we've seen how we can do polymorphic types like alpha to alpha, which are mostly out of like, in our type inference thing we saw, it was because we didn't specify anything. We didn't constrain the input. But it doesn't have to be functions. We can have values that are not functions that are also of polymorphic type. Why? Because empty, right, is of a polymorphic type. It's of type alpha tree. Or nil is also of type alpha list, so on and so forth, right? So I'm showing you that like we can get polymorphic types through a bunch of different ways, all right? Yeah, and then let's see. So for instance, yeah, we can also do this thing where I say that I have nil, which is of type alpha list, and this will actually compile. And then I decide to cons 1 onto L, and I cons y onto L, okay? I should say explicitly, like, this is not a contradiction, okay? Because you might think, oh man, I have a constraint that L should be of type int list, and I have a constraint that L should be of type string list, so then this will not type check. It will, because this is a use of L. At this use of L, we can use it at a different type. Actually, wait, hold on. Yes, so in particular, what I wanted to say is that these instances of L have a type which is an instance of alpha list. This instance of L has type int list. this instance of L has type string list. When I use my polymorphic value, I can use it at different types. Okay, it's different than when I define it. All right. Let's see. Wait, hold on. How far am I through? Okay, cool. So this is important for me to tell you that we have this idea of a most general type for an expression. Okay. For instance, if I had like nil, which is of type int list, right? Or it's of type string list, and so on and so forth. I can write all of these things as true. I can write this, but it only has one most general type, which generally will be what we ask you for on an examination, though not your next one, because this is not part of it. This is the most general type, because every other type that nil could have is actually, I'll say, an instance of this type. And I think I make that concrete on the next slide. So a type T1 is an instance of a type T2 if you can obtain T1 from T2 by substituting for some type variables. Okay? So int list is an instance of alpha list because I substitute int for alpha. Bool list is an instance of alpha list because I substitute bool for alpha. So on and so forth, right? This means that every type is an instance of alpha. Okay? But for instance, let's work through some. So int is an instance of alpha. Int list, instance of alpha list. Int star int is an instance of alpha star beta. Tuples are instances like this. A polymorphic type like beta star alpha can be an instance of alpha, which is anything, right? And you can instantiate it with lists too, right? This is I think you kind of intuitively get this, but I'm giving you this vernacular, okay? Instances. This will be helpful. I'm getting a lot of mileage out of this thing. I made this like for one of your things like the second lecture maybe, and it took me like 30 minutes. And I've just been copy pasting it and switching things around a little bit ever since then. Because this comes up a lot. So we have our giant type alpha here, and an instance of it might be alpha star beta or alpha list or alpha tree. And instances of those might be int star real, bool star beta, int list, unit tree, int tree. Does everyone see why like this, the arrow points to an instance always, right? And in particular, you'll notice that only bool star beta has further instances. Because the rest of these guys don't have type variables in them. They're monomorphic, we'd say. Okay, that's the fancy way to say it. It's monomorphic, not polymorphic. Impress your friends. Yes? Yeah, it's transitive, yeah. So like your int list could also be an instance of alpha. Yeah, good point. Look at that. Cool. Yeah. All right, let's move on. So the most general type of length, for instance, let's give you another example, would be alpha list to int, because it has type int list to int, it has type string list to int, but they're all instances of alpha list, okay? Does that make sense to everyone? Like, you see why the most general type of length ought to be that. Do not say the most general type of something is alpha, all right? Because sorry. I don't remember what I just said, but do not say that the most general type of something is always alpha. Everything is an instance of alpha, but it doesn't mean your most general type is. What I mean by like that is like, if I have length, any type that, like any instance of this function is a type I can use it at. It would not be correct to say the most general type of this is alpha, because I can't use it as alpha. If I use it as this, that means I could use it as int, I could use it as bool, and you can see why that's kind of absurd, right? This is a function, like you shouldn't be able to do that. So instances are things that we use to get the most general type, which is this. Okay? And there are examples as well, but yeah, this is just lingo, all right? This is the most general type. That's the important part, okay? All right, I also should tell you, don't make this mistake on your proofs. So suppose we want to prove a claim like length of L append R is length of L plus length of R. For all L, for all R, etc., right? I want to prove this for length, which takes in an alpha list, okay? No longer are we doing our proof on int lists, we're doing it for alpha lists. You might want to write this. Base case, L is equal to nil. We proceed by structural induction on L of type alpha list. Does anyone see an issue? This is kind of subtle, all right? Why might there be an issue with this? What do you think? So, yeah. You know. Yeah, that's pretty much close enough to the what I was looking for. Basically, there's you know, there's precisely one value of type alpha list. Like I'm saying for all values of type alpha list, let's induct on it. But how many values are there of type alpha list? There's precisely one, I'll tell you. It's this guy. So actually, yeah, you have, that's a good explanation. How do I go to my next step? How do I like take any value of type alpha and cons it on? There aren't any. I told you that. There are no values of type alpha. I cannot, my induction's pretty weird because like I'm doing it over this. So what I want you to do instead is this, all right? Blah, blah, blah. Let T be a type. When you start the proof, we're going to instantiate some random type T. Same way as we said when we were describing the type of cons originally. Let T be a type. We're going to induct on L of type T list. For some type T, let's just say we're inducting on that, okay? Now I can treat it generically because I used to say, okay, let's just cons on something of type T, a value of type T. So now my proof is essentially many proofs. I'm doing it for int list, I'm doing it for string list, I'm doing it for alpha list, but I'm not doing it on like values of type alpha list. Does that make sense to everyone? Do you see kind of like the distinction here in this induction? Okay, like this proof is many proofs. This is the way I would think about it. It's like I'm doing many proofs by instantiating a variable T. Okay. Do this, otherwise you will get points deducted. Okay, it's not a threat. It's a warning. Those are different things. I feel like a bad guy now. Whoops. Let's do okay, wait, hold on. Yes, I already told you all this. Okay, here's what I want to tell you, which is that a polymorphic type is a family of types, right? Because it's like alpha list is a family of types, which is like int list and bool list and so on, right? A function with a polymorphic type, like length, is a family of functions. It's an int list to int function. It's a string list to int function, so on and so forth. And a proof on a function with a polymorphic type, like this, is a family of proofs. It's a proof for every single type. When I say family, I mean like a grouping, right? That's just like something I kind of wanted to have you conceptually understand. I'm running low on time, but this one won't take very long. Okay, actually, I think I have just the right amount of time to do this. Cool. So let's talk about polymorphic sorting. I promised you I'd talk about this. So sorting, we talked about how we can do it on ints, but we're not always interested in sorting on ints because we might want to do more particular things. Let me, actually that was the wrong way to start off. Let's suppose we want to sort an arbitrary alpha list. So I want this function. I want sort of type alpha list to alpha list, okay? How do I implement this function? If I want to do like the merge sort thing, okay? If I went and like I defined merge sort for you on the board, okay? What we would find is that we'd have an issue. Because at some point, I'm going to be holding x and y, where both are of type alpha. And I want to compare them. What do? I can't do this. Because now this will mean that they're ints. Like, do you see the issue, which is that like somehow I have to sort these things without ever looking at what is inside. Because if I ever make an assumption on what's inside, I'm going to get that it's suddenly monomorphic. I'm going to constrain my type and make it no longer general. So I want to be able to sort anything. Yeah. Yeah, so we're gonna do something like that. Yeah, that's the right idea. So we can't. So first of all, this sorting function is impossible to write. I'm gonna give you another way to think about it. It's ill-formed because what does it mean to sort an alpha list? Like in int list, what is the canonical way of sorting ints? Like that, it's kind of biased of you to think that like the normal less than relation on ints is the right way to sort it. What if I want to sort it mod 12? What if I want to sort it in reverse? Like we didn't specify that. So let's specify. Let's be specific. We're going to talk about sorting with respect to a particular comparison function. So we'll say that a function f of type t star t to order, remember the order data type, less, equal, or greater, that is a comparison function if it's total and it defines a total order. Math people are excited right now because this is what a total order is, okay? I'm not going to tell you what it is, but a total order is basically something where if I put all my stuff on a number line, okay, my relation obeys this. Like if this is farther left than this, then it's less. If they're equal, then it's equal. Okay? That's pretty much all you need to know. We can't induce cycles. Like I shouldn't have that this is less than this, and this is less than this, and then this is less than this. Right? I can put it on a line is the idea. That's a total order. All right? So like less than on ints is a total order. Okay? So for instance, valid comparison functions might be this one. We have rev in compare, where if x is less than y, we return greater, otherwise we return less. So you see how this reverses that relation? And it never does equality, because I don't actually really care about it. And then mod 12 compare says, we compare x and y, but only mod 12. So like, we'd say that 2 is less than, I don't know, -1, I guess. This is not valid syntax, but like, you get the idea, right? We might want to do this comparison with respect to a particular comparison function. All right, so these are comparison functions. What do we do with them? With a CMP value of which is a comparison function, here's what we're going to define for it to mean for a list to be sorted with respect to that comparison function. A list L is CMP sorted with respect, again, to that value CMP. If 3 things hold. Either L is nil, in which case it's vacuously sorted, or it's a singleton, in which case, again, it's vacuously sorted, or the first 2 things are sorted with respect to each other. It's less or equal. They're related, right? And then also, y cons x's is CMP sorted. So if I had like x1, comma x2, comma x3, let's say, xn, I want to have that, like, this edge on this like thing between them is LEQ. And if I have this as LEQ, then I want to recursively do it such that this is also LEQ. And then this, and then blah, 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 blah. And if you believe me about total orders, one thing they are is transitive, which means that if this is less than or equal to that, then by our comparison function, this must be less than or equal to that. Does everyone kind of pictorially see why this definition defines a sorted list? Small note about like recursive problems, recursive solutions, which I put at the top right here, but I rarely ever acknowledge in lecture. Lists are really nice because we can define stuff on them just by doing recursion. Okay, it's really easy to say something about like, is a list sorted? Because we just give 3 cases. Okay, just a random small note. Okay, so if I want to sort relative to a CMP function, I have to know what that CMP function is. So we're going to adjust the type of what our sorting function is. Instead of saying that sort is of type alpha list to alpha list, we're going to do this. Sort alpha star alpha to order star alpha list. I'm taking in my comparison function as an argument, okay? But why can we do this? Okay, like, does this feel weird to you? We've almost never done this in this class, I'm pretty sure. Oh my god, I get to say it. I get to say, functions are values. I'm not wearing the jacket today, but functions are values, oh my god, meaning we get to give them as arguments, same as any other value. So I get to take in my comparison function as an argument because that's just something I get to do. It's a value. A value is a value, all right? Just be a rock. So this is fine to do. And now we're promising that the output is CMP sorted with respect to the CMP function. So let's rewrite our, and this is just some stuff about how functions are first-class citizens. I'll let you read over that on your own time, okay? So here's our new specification. Sort takes in 2 things, an alpha list and a comparison function. And I guarantee that, that's supposed to read sort CMP comma L. But sort CMP comma L is a CMP sorted permutation of L, okay? All right, does that make sense? So let's do it. We're going to implement it via msort. And you're thinking, Brandon, you have 3 minutes left. How are you going to define the entirety of msort? I'm not. Here you go. This is msort. I know it's small. I know it's small, but if you remember the msort thing, here's what we're going to do. A hop, a skip, and a jump. And I've nicely highlighted the parts that changed for you. The only thing that changed is msort now takes in a CMP argument, which is that comparison function, and I pass it down. I pass it down to merge, I pass it down to msort, and I pass it down to msort. And then merge uses the comparison function. You see here, instead of x less than y, I do CMP x comma y, and I case on that, okay? I've changed very little of this code, okay? But all of these things changed, all right? And most of it was me passing down the CMP function, okay? But now, msort can be with respect to any comparison function because I use it when I need it. And now this is more general than our idea of sorting with msort earlier. Let's see how we can define sort. Here's what we do. Sort is given CMP and L, and I return to you msort of CMP comma L. And now I'm going to tell you that msort, let's say old, which is like what we defined last class. Yeah. It should be essentially equivalent to sort int.compare L. Okay? Our old M-sort with respect to specifically integer comparison is going to be the same because I didn't change much about the code. But now it's so much more extensible. I never have to rewrite another sort because I just have it here. This is my sort, and it's every sort. I've defined a function that sorts things, but it sorts anything. And the syntactic overhead on that is very, very low. Because what do we get out of this? Code reuse. This makes our lives so much easier. So we can do like compare and then string.compare and revint compare. Okay, cool. Thank you so much. Please fill this out. Worth noting also, Go didn't have this until very, very recently. Like the Go language made by Google, they just straight up didn't have generics or parametric polymorphism. So this is not yes, this is stuff that was discovered 60 years ago. But guess what? We're ahead. They're catching up. Recurring theme.